MMC 225XE pistons and non-ferrous high thermal conductivity compression rings.
Thank you, Paul. Is this working?
It's working now, yeah.
Yep, okay, thank you. Thank you all for coming. As Paul said, my name is Scott. I'm the Technical Director at Alcon Specialist Engineering Products. I've actually got two projects to talk about today. First of which is looking at metal matrix composite pistons, and the second one is looking at a non-ferrous based compression ring. These are, if I start with the MMC, we just completed a 2-year project. The project was looking at 225XE pistons, in particular looking at getting some cost out of the piston, but achieving 90% of the performance in terms of its mechanical properties. Also looking at optimising the piston design in terms of exploiting the benefits of the 225XE, looking at the forging process and creating a neck-shaped forged undercrown and potentially a crown as well, optimising the machining process. And MMCs, so we've been machining MMC now for some 7 years, but looking further at how we can just develop that for volume production. Carried out a life cycle analysis in terms of CO2 footprint, and then demonstrated a commercially viable proposition and route to market. So the partners we had on board were Jaguar Land Rover. The lead partner was Materion, who supply high performance alloys. They supply the MMC, and they also supply copper-based alloys. Advanced Forging and Research Centre, Strathclyde, and ourselves. I'm not a metallurgist. We have Stefan here in the audience actually, who's from Materion, who can answer any questions in terms of the materials. But metal matrix composite essentially is a case of taking aluminium powder. It's mixed with silicon carbide, and it goes through a process of hipping. We produce the billets, and those billets are forged. So in terms of the 90% performance, we were comparing the alloy to a 225XE, which is an alloy that's been used for a long time, and we were looking at trying to achieve 90% of that performance at 50% of the cost. What we actually got to was very close to that, about 4% lower yield strength, very similar in terms of the elastic modulus, and the testing was carried out at Materion and also repeated at Jaguar Land Rover, so at 2 different sites. So in terms of our target achieving the 90% performance, we achieved that essentially. The baseline alloy that is used by Jaguar Land Rover is a very high performance cast alloy. That alloy, when you compare it to the new material that we've developed, we achieved a 44% improvement in terms of the Young's modulus. Very similar in terms of density, proof stress, nearly 100% more. But probably the most important one, and one of the reasons we look at using MMC for pistons, is its high temperature fatigue strength, which is significantly higher, 84% higher than the standard material. Other benefits include thermal conductivity, so thermal conductivity is higher. It's something that we look for in a piston alloy. Coefficient of thermal expansion also greater, so you can better match the bore. So we start with a smaller clearance when it's cold. And it's harder, which gives us some good wear properties. So why are we using MMC? Well, we started using MMC in motorsport some time ago now, until it was banned essentially because of the modulus rule. We've been using it over the last 7 years in automotive applications where we're looking for a very robust solution. So we use it in engines where, especially test engines where knock and combustion problems are an issue, so where there's likely to be pre-ignition, likely to be knock, or we're carrying out studies of that nature. They've just been proved to be very robust. So very good high temperature fatigue strength. The specific stiffness is a lot higher as well, so that for the same fatigue strength as a standard alloy, you can basically reduce mass. One of the main things we also look at is reducing the crevice volume. And what we've been able to achieve, especially on high specific output engines, is a much smaller crevice volume. So in this particular engine, of JLRs, they have a steel ring carrier to protect the top ring groove. We were able to remove that steel ring carrier and also move the top piston ring up. Crevice volume is very important in terms of helping improve efficiency, combustion efficiency, and we found that it's even more sensitive on boosted engines, basically, on very high specific output engines. From a tribology point of view, the finely dispersed silicon carbides offer very good wear resistance. So the top ring groove that we'd ordinarily look for maybe anodizing, or we'd look for a steel ring carrier, we can just remove that completely, and it's proved to be very, very successful. One of the things we tend to do when you're optimising it for mass, you can reduce the compression height of the gudgeon pin, and that gives you two opportunities there really. You can either have a longer connecting rod, potentially less friction, or you could reduce the cylinder block deck height. So it offers some opportunities, but essentially ends up with a lighter piston. It's very good in terms of corrosion resistance, and in terms of manufacturing, it's very good from a forging point of view. We've perfected the machining of MMC over the years now, so we're very happy to machine it. So, bottom line is, from all the testing we've done over the last 7 years, there's been a lot of interest from vehicle OEMs. One of the biggest problems has been the cost, really. It's a more expensive alloy. However, part of this project was looking at reducing the cost of the alloy. Moving on to the piston design, so we took the standard piston from JLR, and then we had some fixed constraints, so we had to maintain the same piston crown detail, pin bore diameter, piston bore diameter, crankshaft offset, pin offset, and the same ring pack groove, and we basically optimised the piston to achieve the same fatigue safety factors for the same loading conditions. So we went through about 19 different iterations. Some of the problems that we're faced with when we're looking at downsizing engines or very high specific output engines is piston fatigue life. That's one of our main considerations. Piston top ring groove wear, and potentially micro welding as well. But generally speaking, if we're increasing the specific output, it generally means an increase in mass for the same piston material. And sometimes a compromised piston ring position, sometimes higher flow to the cooling jet to the underground. There's also more likelihood of abnormal combustion, knock. If it's a boosted engine, then you tend to be knock limited. This particular engine runs on 95-1 fuel, and it is knock limited. End gas temperatures are increased. Top crevice volume is also more sensitive as well, so we find that changing the volume of the crevice volume makes quite a large effect on its performance. So all else being equal, it tends to be reduced combustion efficiency. So although there's some benefits to downsizing, there are some adverse effects. So the piston design that we came up with, in terms of mass, the baseline piston was 456 grams. We reduced that by 15% to 388 grams, whilst achieving the same fatigue safety life. So it's a considerable saving. In terms of the compression height, Paul, do you know how to get the laser working on here, sorry? Green one, okay. Cool. In terms of the compression height, a 3.3mm change, so the piston pin has moved up. So this is the standard piston. This is our new piston design. Pin ball's moved upwards. The other significant change is the top ring groove, which has moved upwards by 1.3mm. That's a significant increase in the piston ring groove. The crevice volume, as a result of increasing this, is reduced by 101mm cubed, so 20% saving in crevice volume, which is a very significant number. You can also see that the skirt's been shortened, so it's a shorter piston now as well. It can support the load still. Looking at some of the potential benefits, so in terms of crevice volume reduction, we've done a reasonable amount of work on this. This is a study carried out with somebody else actually, but making some assumptions for the efficiency of the engine and taking an engine with an efficiency of around 25%, the 20% reduction in crevice volume that we carried out manifests itself into about a 3.75% improvement in BSFC, which is a very, very significant improvement. And as you can see, it's very sensitive. So this graph here shows the relative indicator efficiency change. So a 1% improvement was gained by a 20% change in the crevice volume. So it's a significant number. If you equate that to, again, making some assumptions, if you equate that back to a vehicle, 4.6 grams of CO2 per kilometre, it's again a very, very significant number, all from a change in crevice volume essentially. In terms of reducing the reciprocating mass of the piston, it's always a difficult one to predict its effects in terms of friction. FEV carried out a study on lots and lots of engines over the past decade or so, and reducing reciprocating mass, this is the effect of a percentage reduction in friction, what that means in terms of a fuel consumption saving. So where we've saved about 15% mass, there's potentially a reduction in CO2 of about 1.2 grams of CO2 per kilometre. It's very much dependent upon the engine, whether you've got an offset crankshaft, offset pin, but it's only indicative, but the bottom line being that a saving in reciprocating mass tends to be an improvement in friction. Always a really difficult graph to show really, but potential gains from combustion efficiency and friction from simply changing material are quite significant, and as ever, these gains never really add up, but directionally there's some big improvements to be had from switching material to MMC. And on 4 or 5 of the programs we have running with MMC, we've seen very, very similar gains. So they're significant. Moving on to the piston ring. So the piston ring study we did, again, was a study we carried out for Materion. This is for the American group, again, who make high performance alloys, copper-based alloys. This was a really exciting one for us because it's a non-ferrous based alloy, so there's no iron in it at all. What we were looking to do is basically we were looking at reducing the peripheral temperature around the peripheral of the piston, and looking at reducing piston temperature basically, and looking at its effect on knock. So we set out, we're doing a heat transfer analysis, then some single cylinder engine testing, and the objective was to predict how piston temperature is affected with the application of this new alloy called Performet. It was then to carry out some basic engine testing, actually 2 alloys we tested in the end, and what we asked ourselves is, can we extend the limits of the combustion system? Can we increase BMEP? Can we improve and extend the knock limit of the engine? So conventional compression rings since 1850s have been made from cast iron, still a very good material, then moved to ductile cast iron. Most of the high performance engines are running chromium steel rings, titanium nitrided faced rings, chromium nitrided and so on. Thermal conductivity of these rings is around about 38 to 50 watts per meter Kelvin. So Performet is a ring which is non-ferrous. It's a metal silicide strengthened bronze alloy, so it's basically a copper-based alloy. It has a thermal conductivity of 160 watts per meter Kelvin, it's about 4 times that of a conventional ring. And it has very similar mechanical properties in terms of tensile strength and hardness. So why were we doing it? We're looking at reducing the end gas temperature, basically, and especially on high specific engines or ones that are boosted, we're looking at basically increasing knock resistance. Reducing piston temperature again, improving fatigue life, so again you can make the piston lighter if you can reduce its temperature. Reducing the top ring groove temperature allows us to push the piston ring up even higher and reduce the crevice volume. Other attributes are there's no coating required with the ring, so it's a ring that's monolithic. You remove a failure mode and potentially reduce the cost as well without a coating. It also has a lower modulus, which means potentially better conformability to the bore. Has a low coefficient of friction. Very good in terms of groove wear, which we'll come on to shortly. and the coefficient of thermal expansion is more matched to aluminium. So the groove clearances to the piston ring, you maintain a clearance. In terms of the heat transfer analysis, we took the boundary conditions from an engine we've worked on over the last 5 or 6 years, which is Ultra Boost. So we used boundary conditions from this engine to feed into our analysis that we did. So it's a very high specific output engine, making 283 kilowatts. The other point to note there is the engine runs pretty much lambda 1, and the boundary condition that we used were actually lambda 1 up to full speed and full load as well, so it's running pretty hot. It's very much a simple heat transfer analysis. We looked at a couple of different cases. The one I'm showing today is a single case where we're looking at Pmax boundary conditions. So shows the piston in the bore. It's about 15 degrees after top dead centre where Pmax occurs. 135 bar cylinder pressure. This engine's been operating up to about 170 bar. So we actually looked at some different boundary conditions with higher cylinder pressures. And the bottom line was we were looking at the effects on changing the heat transfer, thermal conductivity, and looking at its effect on temperatures. So this graph here shows ring conductivity and temperature. So the standard ring is operating around this kind of temperature, and as we increase the ring conductivity, we're reducing the average temperature of the piston significantly, about 10%, by changing the conductivity of the ring. This is an interesting graph again. So basically, we looked at 2 different rings, the standard ring at 38 watts per meter Kelvin and the new ring at 160 watts per meter Kelvin. And we looked at the ring in 2 different positions, a standard position and also a higher position, so we moved the ring up. So for the standard ring, you can see that the maximum temperature stayed fairly similar actually. Top ring groove temperature actually rose, and the maximum ring temperature actually rose. So by moving the piston ring up, we actually got hotter local temperatures. Whereas with the higher conductivity ring, we found about a 10% reduction in temperature. So we're reducing from about 326 degrees C piston crown temperature to 300 degrees C. And by moving the piston ring higher up the bore, we reduced it to just under 300, so 295 degrees C, which again is a significant number. So what that allows us to do is reduce the mass of the piston further to achieve the same fatigue life. And likewise, the actual top ring groove temperature gets cooler as well, so we can move the top ring up even higher. The testing we did basically was a very simple set of tests, really just to prove the durability of the ring, to move on to multi-cylinder testing onto a customer program. So we did a basic break-in prove-out test, 3 power curves, and then we did an endurance test of 5 hours, greater than 90% wide open throttle, and we repeated that 3 times, stripping the engine at each stage to check the parts. We carried out on our own single-cylinder engine, so it's very much a race engine, but has a very high mean piston speed of about 24 meters per second, and it's naturally aspirated. BVP is about 15.5 bar, cylinder pressure is about 107 bar. The standard ring that we baselined it against was a 0.7mm DLC faced ring, piston 2618, anodized top ring groove, and a Nickel coated liner. Here we can see the Performet ring, and that's it in its liner. Some very brief test results. Compared to the baseline test, we were measuring blow-by, crankcase pressure and performance. We really measured no difference in performance at all. In terms of blow-by, very, very similar numbers again. If anything, I'd say the blow-by was more stable. Crankcase pressure remained good as well throughout the 3 endurance tests. Stripping the engine components afterwards, rings looked very good. Probably the most notable thing was the piston ring groove itself was no signs of wear, which we normally get some wear on our standard piston after those 3 durability tests. So in conclusion, Going back to the piston, some significant advantages to be had over conventional aluminium alloys. There are some gains to be had in terms of efficiency. We've shown that we've been able to net shape forge the undercrown and potentially the crown of the piston as well. We achieved our target of 90% performance and 50% of the cost. We now have 3 or 4 customer programs underway and looking to commercialise it initially on some niche volume applications. The compression ring is still at an earlier stage of development, but again some really interesting results from the analysis and some of the tests that we did. And what we're now carrying out is some multi-cylinder testing. We have some pistons which are thermocoupled, and we're running some thermocouple tests to correlate the analysis work we did. If that correlates, we then go on to doing some BSFC measurements and some drive cycle work. And again, this is with an OEM. And that pretty much wraps up my presentation.
Thank you very much, Scott, for some very interesting results there.
Thank you.
We are running a little bit late, but if there's perhaps a chance for one question, if anybody wants to ask something before I move on to the next speaker.
If anyone hasn't got any questions, we're on the stand just to the other side of the, just to the far end of the hall, back there basically.
Right, okay, thank you. Well, in that case, thank you very much again, Scott.
Thank you.
We'll move on to our final speaker for this morning, who's Dr. Leonard Klaus.